All right, everybody. Happy Friday. Also, I'm still trying to get everybody's names down, so please don't be offended if I call you by the wrong name. That's not intentional. Or if you have a preferred name, and I call you by your name that's on the call sheet, just let me know. I think I called Gloria Olivia the other day. So please just I would rather not call you by the wrong name. So it's less embarrassing for all of us if you just correct me. With that in mind, random question. How does static electricity work? Well, it'll make more sense when we start talking about atomic structure, which will either be the second half of today's lecture or it'll be on Monday. But basically, when two different materials rub against each other, you actually kind of it's almost like friction where you get some of the electrons from one object transferring to the other. The same way that when you rub sandpaper on wood, you get sawdust on the sandpaper, right? So you actually wind up building up electric charge because you get extra electrons on one of the materials and less electrons on the other material. When that gets to be a large enough difference, then the attractive force from the extra electrons being attracted to the object that has too few electrons, they actually will leak through space. And that's what lightning is, basically. Not basically, it's exactly what lightning is when you have electrons from one cloud that has too many electrons moving to a cloud or to the ground that has fewer electrons. So when you actually rub your socks on the carpet and generate static charge and then shock your sibling, I don't know if anybody does that, I did to my little brother, then that's actually literally what you're doing. It is actually the same process as lightning, just on a much smaller scale. In different materials, that works better too, which is why some jackets, if you wear some jackets, you'll notice right away, like you get, your hair sticks out, that kind of thing. And other jackets, it doesn't. It has to do with the difference in how well those materials hold on to their electrons. The classic example was Ben Franklin, and I believe he used rabbit fur in glass. You rub rabbit fur on glass is one of the ways that or maybe it was rabbit fur on silk. Rabbit fur on silk, right? And you actually generate a fair bit of static electricity pretty well, and that's how we started studying electricity, and that's what led to the whole, kite in the rainstorm incident. And another fun fact, that's the reason why electrons have a negative charge. It's actually all Ben Franklin's fault. When we start counting electrons, you'll notice that there's a negative charge where it would make more sense if it was a positive charge. It's because Ben Franklin didn't know at the time what he was doing because he didn't know what an electron was. So he just randomly said, okay, the charge that's on the rabbit fur is positive, and the charge that's on the silk is negative. And if he'd switched those, everything would make more sense. But he didn't, so we get to blame Ben Franklin for when you give something a positive charge when it should have a negative charge. Somebody else asked about learning in my free time. I'm of the opinion that everything you can do that uses your mind is a form of learning. You might be learning about something that's not particularly useful, like say, I don't know, the lore in Minecraft. It's not necessarily like a transferable skill. Very few people, when you're applying for college or for jobs, are going to care if you know what an Enderman is. But on the other hand, you're still learning, you're still thinking about things. So that kind of, I like doing activities where I get to use my mind. But I'll pretty much only read fiction. I don't really like reading nonfiction in my spare time. So I wouldn't call that necessarily learning, but it's still using my mind, getting better at certain skills. Last but not least, what's the hardest class I took in college? The most comprehensive class I took in college was a class called Organic Qualitative Analysis, which was a senior level class in college. It was a lot of fun because I'd taken 3 years of organic chemistry by that point, and it was basically a class in identifying random compounds. And so the midterm and the final were literally Here's a vial of white powder. What is it? And there was a list of about 100 pages of compounds at the back of our textbook that it could have been. And so we just got a week with that to try and figure out what it was. And if you got it right on the first try, you got 100% on the final. And if you got it right on the second try, you got 90%. And went down from that. That was a really fun. I wouldn't say it was the hardest, but it was definitely the most comprehensive because we had to use everything I'd learned from the previous 3 years. The hardest class I took was probably either numerical methods, which is the class on how you can do math when calculus doesn't really work the way it's supposed to with functions that don't behave, so you can't actually take their derivative or their integral. You have to use what are called numerical methods, which is basically just a way of getting an answer by rounding instead of getting a true answer, the way mathematicians would like to do it, which is called an analytical solution. A numerical solution means we got a number, but it's not really the real number. It's just an approximation. And I took that without having the prereq when I was in grad school, and that was a mistake. But the only class that I ever had to retake was also in grad school, and it was because I made a dumb decision on one of the homework assignments and turned in my friend's results as my results. We had to write code in a statistical mechanics class, and I wrote my own code, but I didn't leave enough time before I had to submit my assignment for my code to actually run. It needed about 45 minutes to run on the computer so I could get my results. And rather than turn it in late, I took my friend's figure and turned it in with my code. So I cheated and got noticed because my friend's code was wrong. So I turned in a result that was wrong. And when you get two identical wrong answers for something that's supposed to give you a somewhat random answer, it's really, really obvious. So I retook that class in grad school as a result. And so that was a tough lesson to learn. I wouldn't say the class was that hard, but I made it hard on myself because I had to take it twice. So don't do that. Learn from my mistakes. Don't turn in somebody else's work as your own. And honestly, I probably would have been fine if I had just written, this is not my figure, but this is what I think it's supposed to look like, but this is my code. If I'd acknowledged that it was not my figure when I turned it in, I probably would have been fine. Right? So if you use somebody else's work, acknowledge it. All right. So there's 3 answers for that one. Let's do a little practice. We ended by very quickly talking about higher powers of units the other day, right? And we said, okay, well, if we wanted to convert a box that's 1 foot cubed, and we wanted to know how many cubic centimeters that is, how would we calculate that? Diego? Bryce? Either way.
Set it to inches and then try to convert.
Right, we want to go inches to centimeters, but our conversion is not feet squared, so we have to do it 3 times, right? We can say 1 foot is 12 inches. That's the conversion we all know. There is an exact conversion for cubic feet and cubic inches, but that's another thing to memorize. So instead, it's more helpful if we just remember we can do that. So it's going to be 12 cubed inches cubed is equal to 1 cubic foot. What do we get for an answer there? 1,000 and maybe 1,600, something like that. Maybe 2,000. Who's got their calculators out? What's 12 cubed? 1,728. That sounds like a power of 2. Yeah, that seems reasonable. And considering cubing double-digit numbers in your head is not my forte, I'm going to say 1,600 is pretty close. I'm going to count that as a win, especially on a Friday afternoon. So then all we have to do to get it cubic inches is do that one more time, right? So I'm showing all the steps here, but you can do them both at the same time. 1 inch, 2.54 centimeters cubed. So 2.54 cubed squared is like 8.5 times another 2.5. So something like 20. So 1728 times about 20. So something around 30,000. That doesn't seem right. No. Say it again. I'm just gonna say 2.83 times 10 to the 5, 4. That seemed like a reasonable number. That seems like a lot of cubic centimeters. What does 1 cubic foot look like? That's about 1 foot cubed. So something like that. I don't know. Does that seem like it's too big of a number? Maybe not. These cubed conversions wind up being bigger than it seems like they should. But volume is like that. Volume is weird like that. It gets big faster if you're growing in all 3 dimensions. I think we did all the math right. I don't see any place in here where it looks like our answer, we input anything wrong. All right, so let's do another practice. We start in cubic centimeters. 7.68 centimeters by 12.45 centimeters times 5.56 centimeters. Finding the volume in cubic centimeters is easy, right? Length times width times height. What do we get? $61.9 after we round, right? We're only going to keep 3 sig figs because we have 3 sig figs times 3 sig figs times 4 sig figs. So our answer is going to have 3 sig figs. That doesn't seem big enough though, does it? 513, 532. That sounds familiar.
Yeah.
All right, we want to find that in liters. How do we do that? 1 milliliter is 1 cubic centimeter. This is one of the reasons I want to do this example, even though we just did an example, is that that's one that we're going to use all the time. 1 cubic centimeter is 1 milliliter. It's 1 to 1, and that's exact, not approximate. It's the definition of 1 milliliter is 1 cubic centimeter. So technically we should show our work for that, but as soon as you're comfortable using that conversion, you don't even need to show that one really. 1 cubic centimeter is 1 milliliter. Cancel out the units, we're left in milliliters. Easy enough, right? And now for milliliters, we can actually go to liters really easily, right? Milli is a prefix meaning 1,000, right? So 1,000 milliliters is 1 liter. So we're going to get 0.532 liters. How come I didn't have to cube this conversion? Because it's already got cubed as part of the conversion. We only need to cube the conversion if we're doing, say, a length conversion, like 1 inch over 1 is 2.54 centimeters. If our conversion only has 1 power of centimeters in it, but we've got centimeters to the 3rd power here, then we would need to cube this entire thing, right? Let's use the same number and put it in another context. Let's do it in cubic inches. How do we get to cubic inches? Well, we had cubic centimeters right here, right? So 532 cubic centimeters. I keep trying to do that today. 2.54 centimeters is 1 inch. Cube the whole thing. What do we get? Something like 30, if I'm remembering right. Been 4 months since I did this practice problem, so 32.5. Thank you. Now, if I want to put that in gallons, on your conversion sheet, you have gallons, and gallons is also on the slide right here, right? Just to reiterate, it's 231 inches cubed is 1 gallon. Are we going to cube this one? No, because inches cubed is already cubed. All right, so we'll get something 0.1 something, right? Give me 2 more sig figs. 4.1. Thank you. So some of the imperial units, you can kind of see where they came from. Like a foot is literally the length of a person's foot when they first defined it, probably a nobleman or something. And then an inch is about the width of an adult male's thumb, is about an inch. I have no idea where the definition of a gallon comes from or why it's 231 cubic inches, but it is. Does anybody know where an acre comes from? An acre is an area unit, right? You know?
It's the amount of time that like thinking box can like do in one day.
Close. It's the amount of land that you could plow without an ox in one day. So one person plowing, they didn't always have animals to hook up their plows to. So they would actually pull the plows themselves. And it's the amount of land that one human adult could plow in one day was defined as an acre. It's about 43,000 square feet. 43,000, 46,000, 43. Doesn't matter. All this to say, I don't know where 231 cubic inches comes from, but this is exact because it's a conversion within the same unit. Or sorry, within the same system. So because inches is imperial and gallons is imperial volume unit, this is an exact conversion. There's some similar story about miles too. Mile is distance between two points in a village in England at some point. All right. So how do we feel about these higher power units? They're not too bad, right? If you actually list of unusual units, there's another good one related to acres. You know, anybody know how they measure the volume of lakes? What unit they use? Sometimes it's like square miles or cubic miles, but cubic miles is really too big for most lakes. Leagues is a nautical unit. I always mix up with fathoms. A fathom is 6 feet. A league is distance, not a volume. Traditionally, they use acre feet. So if you picture an acre of land, a foot deep is a volume. That's actually how they look at how big a lake is. They rank it in terms of acre feet. Except for Tahoe, because it's too big for that.
So smaller than that.
That's a good question. If you talk to people from Minnesota, any body of water that's like larger than classroom is a lake. But they still call it a pond when it comes to playing pond hockey on them. So I think that's just colloquial. You play pond hockey on a lake, but everything is a lake, whether it's actually a pond or not.
But Tahoe wasn't measured.
Cubic miles mostly because it's too big. That or cubic meters. cubic meters is going to give you a really big number. One of your homework problems in the next couple assignments is here's that I think the volume of Lake Tahoe is 36 cubic miles. Convert that to some other volume units. But basically, there's a couple lakes in the world that they still consider lakes, but we don't really measure their volume in acre feet or anything like that. All right. Other weird units. If we want to convert combined units, there's a couple ways to do that. So for instance, say we had 22.0 meters per second. We measured somebody running and we wanted to convert that into, say, kilometers per hour. How can we do that? Do one at a time. You could say 22 meters and convert 22 meters to kilometers, and then you could say 1 second and convert 1 second to hours, and then do the division. That's the way it's easiest to understand it. 22.0 meters per second means 1 second equals 22.0 meters, right? So if we just said 1 second, we convert that to hours, and then another 60. We get something 1 divided by 3,600 is how many hours is in 1 second, right? So 0.003, no. Thank you. And then it's a 3. How many sig figs do we want to keep for this? More than that. Good answer. Those don't count. Our 22.0 is our actual measured number here, right? We're assuming the 1 second is exact. So let's carry at least 3 sig figs here. 0, 0, 0. Is it 3, 6?
2 7. Oh, or like 0.000 2 7 7.
Hours. Oh, luckily the next one's easier. 22.0 meters. If we want to put that in kilometers, what's our conversion? 1,000 meters is 1 kilometer. So how do we get our final answer? We just put them back in the same ratio, distance over time. 0.0220 kilometers over 0.000278 hours. Yeah. Here? 22 meters should be 0.02. Yes, there you go. So what do we get for an answer? Something like 6, or the other way, 60. 79. So these you can think of these as really they're 2 conversions in one, but there's nothing tricky about either of them individually. Converting from seconds to hours is easy. Converting from meters to kilometers is easy. The trick is just knowing that you then have to take those answers and put them back as a division problem. The other way you can show your work with this, you can actually do this all in one step on your calculator. if we write it like this, if we want to cancel out seconds and be left in minutes, it's basically just going to be everything backwards, because seconds is, if seconds is on the bottom here, we're just going to put seconds on the top here. Right, and then our units still cancel out the same way we were used to. So we actually can show all the same steps without having to end with another division problem. So minutes, so then 60 minutes, this goes on top, 1 hour on bottom. We just ended there, we'd be in meters per hour. And then last thing, we want to cancel out meters as well. So we're going to put 10 to the 3 meters is 1 kilometer, just like we did before. So you can show it all as one step. There shouldn't be any difference in your answer other than maybe a little bit of a rounding difference between those 2 steps. I tend to think of it like this because it usually means less writing and less time with the calculator, but it makes no difference as far as the logic and the math steps involved. All right, so here's the showing it the other way. Seconds to seconds, minutes to minutes, and then meters. Yeah, it's not to give you kilometers. The way I was originally taught is that to always do the unit that's on the bottom first so that you don't forget to do it. But it shouldn't make any difference mathematically if you convert the bottom unit first and then the top, or the other way around. Just don't forget. All right. Questions on conversions? How are we feeling? How did yesterday's lab go, by the way? Get through most of the data at least? It's just measuring stuff, right? Takes a little bit of practice to make sure you get the right number of digits, but it's nothing inherently tricky about it once you get it down. It's one of those things, if you spend the time and get it down, you'll never really forget it. It'll just become second nature. Side effects may include being angry when uncertainty is not presented properly. Once you learn how to do it properly, but that's going to happen anyway. That's just like, you know, somebody who knows about science getting mad at Star Wars physics. Occupational hazard. So we wanted to convert 65 miles per hour into feet per second. Could we do that? Hours to seconds, feet to miles, right? So I'm not going to work through that one right now. How about if we want to do something like price of gas? You can tell how old this slide is by the fact gas was only $3.26 at the time. We wanted to convert $3.25.9 in US dollars per gallon of gas into euros per liter. Anything different about that compared to what we just did? Not really, not once as long as we're given the right conversions, right? You need to know a conversion for euros to dollars, which again, that's also probably out of date at this point. But we can go gallons to liters. So take a second, try this one, and then I'll work through it on the board. $2.259 over 1 gallon. This is one where we might actually want to do the dollars to euros first, just because it's a one-step conversion and then it's out of the way. because we have $1.09 is €1. So that'll take care of that. Now we're in euros per gallon. We want to convert gallons to liters. We're trying to use only the exact conversions that are given. How are we going to do that? Gallon to inches cubed. Now I've got inches cubed on the bottom. To put inches on top. Cube the whole thing. Last step.
Oh, it's the second.
Centimeters cubed to liters, right? So what goes on top, centimeters or liters? Centimeters. We get for a final answer. How many sig figs? Good question. Started with 4 sig figs for a currency conversion. Is that exact? Or is that approximate? It can vary, right? So that's a measured number. So only 3 sig figs in our final answer. 3.71. Okay. So 3 divided by that, right? Or 3.259 divided by that. What's our final answer for the price per gallon or per liter? So 3.259 divided by 1.09 divided by 231 divided by 2.54 cubed times 1,000.
You put the 231 also put in the 3.
No.
You just
So we're
leave
not
it.
going to cube the 231 because the inches are cubed already. Right?
I got approximately 0.789.
7.90. All right, so this is a good practice problem to work through because it involved practicing using this again too, right? Anytime we're converting volumes, got to be aware of that. Pay attention to that, especially if we're trying to go from one system to another system. There are lots of other routes you could have gone with your conversion sheet because your conversion sheet has a quarts to liters conversion, right? But given that you know these ones, Henry, or sorry, Philip,
Why did 3 sig figs instead of 4?
because that's a measured number. Because that's not exact. So that has 3 sig figs, or a price of gas has 4 sig figs. That's going to be the one that limits our number of sig figs for final answer. Anybody in here seen the old movie Office Space? It dates me a little bit. It came out when I was in high school. It's about a couple of people software engineers working on fixing code for the Anybody ever hear of the Y2K bug? And back before you actually had to put in 4 numbers for a year for your date of birth, you only had to put in the last 2. So if you were born in 86, I didn't have to say 1986. I'd say 86. That caused a problem in all the computers when we got to the year 2000, because then you had birth dates that ended in 01, but the computers would interpret that as 1901, not 2001. So that caused a whole bunch of issues with the code where that people had to go back in and fix all the code to require 4 digits instead of 2 digits for years. And they made a whole movie about this process where the 2 of the computers or 3 of the software engineers decided to do all the, anytime you had to round a price or an amount of dollars, they would take the extra digit on cents and they would just put it into, they'd steal it, put it into their own bank account. Except that they missed the decimal place. And so they were actually taking entire dollars instead of taking fractions of pennies. So they got caught really, really quickly. But that's actually a real thing, except that guess what? Banking institutions are never rounding that in your favor. Anytime your interest on in your bank accounts or anything like that generates a fraction of a penny like this, they're always going to round it in their favor, never in your favor. That's just kind of the way banks work. It was actually a real thing that happened back in the 70s, where people, when they first started using software to do banking, where they actually, there were some software engineers who used that as a real scam. And they lasted a little bit longer before they got caught. They might have even gotten away with the money, made it to a non-extradition treaty country. If I'm remembering correctly. Anyway, it's neither here nor there. All right. This is practice using a combined unit as a conversion. So for instance, if you had a speed, we want to do something like how many feet could you travel in 45 minutes if you're going 65 miles per hour? Is there anything inherently tricky about that? Well, you're starting with a time and you're trying to get to a distance. Anytime you're going to start and end in 2 different properties, you're going to have some sort of a weird conversion in there somewhere, right? I mean, speed's not that weird of a conversion. But we can see this with a lot of things. Density is another really common one, right? We've already seen some examples of that. So in this case, if we took minutes and converted it to hours, then we can use our 65 miles per hour as a conversion. We get from hours to miles, and then we can go from miles to feet just like normal. All right, so any of these combined units, this will really show up in ways that will make a lot of sense when we start talking about energies for molecules, because we wind up with energy units that look something like kilojoules, which is an energy unit per mole, which is a way of counting molecules. That's a conversion too. Just a conversion where we don't know what these units are yet, but as long as you've got one type of unit divided by another type of unit, we can use that as a conversion. All right. And we want more practice with these, or should we get to some atomic theory? Atomic theory? We've got time. Let's do one more practice conversion. It involves a gold brick. That's always fun. You got a gold brick. 10 centimeters by 10 centimeters by 40 centimeters. And gold has a density of 19.3 grams per cubic centimeter. How many kilograms are in a brick of gold? How do we get that? What's our roadmap going to be? Start by finding the volume, right? Got dimensions. Volume of gold. From volume of gold, you can go to grams of gold, right? Yeah. Because we've got a density. It's in grams per cubic centimeter. And from there, we can go to kilograms. All right, these are numbers we should be able to do in our head for the volume. What's the volume of our old brick in cubic, 4,000 centimeters cubed. Right, so 4,000 centimeters cubed is going to be, and it's only 3 sig figs though, so 4.00 times 10 to the 3 centimeters cubed. For 1 cubic centimeter, 19.3 grams. And for every 1,000 grams is 1 kilogram. What do we get in terms of kilograms? Something just under 80. That seems pretty heavy. What is that roughly in terms of pounds? About 150, maybe more like 160. What does 10 centimeters by 10 centimeters look like? 10 centimeters is about half of a ruler. So and then 40 centimeters, like 1.5 feet. It's really heavy. Sometimes I have us estimate the size of the golden. Everybody's seen Raiders of the Lost Ark, right? Okay. If not, that's your homework for this weekend. Go watch Indiana Jones Raiders of the Lost Ark. You can tell your parents I assigned that as homework. There's the scene at the beginning where he's got the golden idol that he's carrying around. If you estimate the size of that and use the density of gold, you wind up with that golden idol would weigh about 80 pounds. Which means there's no way he's putting it in his man purse and running and jumping over a pit. That's not happening the way it's drawn out in the movie there. Maybe it might not be solid gold. It could be gold over wood. We'll go with that because I don't want to ruin Indiana Jones because it's an amazing piece of cinema. Here's a bit of trivia. That's one of 2 movies that Steven Spielberg has ever said that he was satisfied with the way it turned out. Raiders of the Lost Ark, and I think Schindler's List. You would think Schindler's List, but he's also a very sticky person. All right. And the other way that you can visualize this is the density of gold is almost 20 times that of water. So picture a bottle of water and then picture it weighing as much as 20 bottles of water. It'd be really heavy, right? All right. Let's talk a little bit about atoms. And pull up the other slides here. There we go. All right, atomic theory is kind of fun because we get to talk a little bit about science history. I like to present the science that we learned in this class with some of the historical context that goes along with it. So this actually goes back a really long time. This thought experiment is one of the ways that the ancient Greeks, based, like I said before, they weren't really doing science because the scientific method didn't exist. But they would basically just pose these thought experiments and then just argue with each other. And depending on who everybody liked more or whose opinion they thought made more sense, common opinion would basically wind up on the side of one versus the other. And so this was the original thought experiment. What happens when we start dividing a piece of copper wire? So if you start with a piece of copper wire and you cut it in half, then you take one of those halves and you cut that in half. You take one of those halves and you cut that in half. There's basically 2 options as you continue to do that. the two options are eventually you get to a point where you can't divide the copper anymore, or you could keep going until the copper is infinitely small. Right? And so here, these are the two philosophers that did most of the arguing about this. Democritus had the opinion that matter is made of small indivisible particles that he called atoms. Atoms in Greek just means you can't cut it, indivisible. Aristotle, on the other hand, was of the opinion that matter can be infinitely small and is made of varying four amounts of the four primary elements, which in ancient Greece was earth, wind, fire, and water. All you had to do was vary the different ratios of those elements. You got all types of matter. Which of these two have you heard of before? You heard of Democritus? Well, that's actually impressive. I had not at your age. Aristotle's the one that most people know if you're not in the science class. Most people, if you gave them those two options, people would think Aristotle. Aristotle was more of a mathematician, and plus he actually had a better, if you want to call it, educational pedigree, because Aristotle was a student of who? Does anybody know? Close, the other one. Plato. Plato was Socrates' student, and then Aristotle was Plato's student. So basically, because Aristotle came from the right background and had already done some work involving math that actually does hold up, Aristotle basically won this argument in the court of public opinion in ancient Greece. It also could be that Aristotle outlived Democritus, because when Democritus died, there's actually accounts. We have very, very little of Democritus's writings, because when Democritus died, Aristotle actually went to Democritus's city, went to the library and had all of Democritus's writings burned. So that's one way to make sure you win the argument, is wait for the other person to die and then just get rid of all the evidence they existed. So Democritus, though, it turns out, so basically Democritus is forgotten for thousands of years until the Enlightenment in Europe, until the 1400s, post-Renaissance. In the 1400s, 1500s, 1600s, some of the rich Europeans found some of Democritus's writings and revived the idea of atoms. Because the problem with this debate is that neither one of them had any way of testing what they were arguing about. Right? So that's what makes it so it wasn't really science. They didn't have any way to actually settle this other than just yelling at each other and waiting until one of them died. So fast forward several thousand years to the Enlightenment, and they started coming up with ways that they could actually test some of these ideas. In particular, there were three scientific laws that they had discovered during the Enlightenment that allowed them to kind of decide between these two ideas. There was the law of conservation of mass, which was put forth by a physicist named Lavoisier. There was the law of definite proportions from a Frenchman named Proust, not the same Proust that's known as the author, different Proust. And then Dalton, an Englishman named Dalton, came up with the law of multiple proportions. So law of conservation of mass, what does that mean? Right. And by the end of this class, we'll actually see where that falls apart. Does anybody know where that falls apart? Yeah. It can be converted to energy. What's the most famous scientific equation from the 20th century? E equals mc squared. E equals mc squared is actually the relationship between matter and energy. It turns out matter really is just energy in a different form. So we'll actually come back and revisit that later. For now, I'll just use that as a carrot. Stick with this class, and E equals mc squared will make sense to you by the end of it. Law of definite proportions basically said that no matter what you do, if you have water and you break water up into individual elements, you always get the same amount of hydrogen to oxygen. You always got for every 2 grams of hydrogen, you would get 16 grams of oxygen. No matter what you do, no matter how big a sample it was or where you got the water, water always had that same ratio. And the law of multiple proportions basically said that, well, if you have another substance, another material made up of the same elements, those elements always combine in whole number ratios. So if you took, instead of taking water, if you took hydrogen peroxide and you split it up into its component pieces, instead of getting 2 grams of hydrogen for every 16 of oxygen, you got 2 grams of hydrogen for every 32 grams of oxygen. So you were off by a whole number ratio. And so Dalton was the one who put all of these 3 together to come up with what he called atomic theory. So he actually went back to Democritus's writings to come up with the word atom. And what he put forth was these 4 premises. Every element is comprised of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from other elements. Meaning that basically if it's a specific element, all pieces of that element look the same. These atoms combine in simple whole number ratios to form compounds. And you can't change one element to another element. You can only change how they're attached to other atoms. Are any of these false? Which one? Number 1, why? You can split atoms. So basically, this is a good example of the scientific method. This worked in the 1700s. This was their best approximation for how matter worked in the 1700s. Fast forward 200 years to the Manhattan Project and Marie Curie, and they started to understand that nuclear reactions actually could cause atoms to break apart into smaller pieces. And that actually means 4 is wrong as well. We actually can convert one element to another element. It just involves nuclear reactions. So we're going to leave that alone again until we get further into the class. Right, but basically, just because we have to amend this doesn't mean that this isn't a good first place to start. A common complaint with chemistry is that you learn something in chemistry, and then the next chemistry class you take, you have to unlearn it and relearn it a different way. Because basically, these are generalizations. And as you take more and more science, you learn where the generalizations fail and how to make them more specific. These are good enough generalizations for 90% of the chemistry we're going to do in this class. Any other amendments that you can draw from your modern knowledge? Anything else that strikes you as maybe not true that needs to be amended?
Are they all?
Good. So whole number ratio, they are all whole number ratios. They just might not be simple in the colloquial, the way we normally use the word simple. Proteins in particular can be really, really big. Proteins can be made of hundreds of thousands of atoms, but they're still going to be whole numbers. So this is using simple in the mathematics sense of the word simple, meaning they're integers. But they can be really, really big numbers. A protein might have a formula that looks like C1118 H 24180. Let's see what else is going to be in there. I don't know, it might have only a couple hundred oxygens. No, how many? Probably 500 oxygens, probably about 618 nitrogens, probably some sulfur in there too. That doesn't look simple, but it's all going to be whole numbers. You can't have a fraction of an atom in a chemical compound like this. So we've said that 1, 4, and 3 are all need some amount of amending. Does 2 need to be amended at all? Can anybody think of anything? Where we can tell one atom of hydrogen, say, from a different atom of hydrogen? Anybody ever heard of heavy water? What's heavy water that makes it different than regular water? Besides heavier. No. If you add an extra hydrogen, you actually make it acidic. Instead of having it be water as H2O, you actually make H3O with a plus, which is actually an acid. But what you do is if you take a hydrogen and you add an extra neutron to the nucleus, well, we haven't even really defined the nucleus yet. That's where we're going next. Basically, the idea that all atoms have the same mass and other properties would be that you can't distinguish any one atom of that element from any other atom of that element. It turns out that's not the case. We have what are called isotopes. And an isotope basically means that you can have certain atoms that weigh more than the same element. So that's actually what heavy water is you replace the hydrogens in H2O with deuterium, which weighs twice as much. But it still behaves like a hydrogen chemically. It just weighs more. All right. So, do I want to get in Mendeleev now? I thought I went this way. We'll come back to Mendeleev. So one of the first places that they realized that the atomic theory fell apart was a physicist named Thomson, I believe he was Scottish, discovered that you could actually make what they called a cathode ray tube. Basically, you just made a tube of glass and you pumped all of the air out of it. So it's almost a vacuum inside the glass. And if you set it up so that you had 2 different metals on either end and hooked it up to a battery, you could actually wind up with what he called cathode rays flying through the vacuum from one metal to the other metal. And a couple of things that he noticed about cathode rays is he noticed that they travel in straight lines and that they have a negative charge. But the atoms that they started from were neutral. And he also noticed that they were 2,000 times smaller than hydrogen. And hydrogen, they already knew at this point, was the smallest element. And no matter what you used as the metals in the cathode ray tube, you got the same particles out of it. You got these same cathode rays. What does that tell us? What does that tell us about atoms are indestructible, small indestructible pieces? You're getting smaller than something that's just one atom. In other words, atoms are made of smaller building blocks. So we defined an atom as being indivisible, and then within 50 years later, they're like, well, except for these other little pieces that we can find. These little pieces are negative. So what did Thomson actually discover? Electron. That's actually what a cathode ray is. They called it a cathode ray like it was light, but it has mass. It's not actually light. It was negatively charged, 2,000 times smaller than hydrogen. That's an electron. This would have been in the early 1800s, I want to say. Maybe a little bit, maybe more like mid 1800s. Well, if the electrons were negative, but the atoms were neutral, what else has to exist? Something that's positive. We had to balance those charges out, right? So Thomson came up with what he called the plum pudding model. The plum pudding model basically said that these electrons were embedded in the atom. But if you put enough force on them by hooking it up to a battery, you could get these electrons to dislodge and fly away through the material. And so Thomson just said that this plum pudding, the stuff that's around the electrons is sort of like this putty, like Play-Doh. And that's all positively charged. And it balances out the electrons that are negatively charged. So they called it the plum pudding model because this is in England in the 1800s. And so their idea of a dessert is what we would call fruitcake now. A plum pudding is basically a fruitcake, which, if you're anything like me, tastes as bad as everything you've ever heard about a fruitcake. Plum pudding is basically just sugared plums in bread. Not my favorite thing. I don't like cooked fruit or dried fruit, let alone both of them at the same time. So Thomson's student Rutherford decided probably didn't decide. He was probably told by his boss, Thomson, his mentor, advisor, to come up with an experiment to test this, right? Because it's not science unless we can test it. So Rutherford said, okay, well, I can take gold. Gold was already known for being extremely malleable, meaning you could make it really, really flat, literally just by hammering it. The word mallus in Latin means hammer. So malleable meant you could hammer it and you could make it really, really thin. So you can make gold foil exceptionally thin to the point you can see through it, actually. So they made this gold foil that was so thin you could see through it. Then they fired particles at it that had a positive charge. And Rutherford's expectation was that when these particles traveled through the material, they were going to slow down and come out the other side going slower. And so he set up a detector over here to determine how fast the particles were going. And so he measured how fast the particles were going without the gold foil. Then he measured how fast the particles were going with the gold foil. Spoiler alert, he found out that most of them were going the exact same speed when they came out the other side. But some small fraction of these particles would hit the gold foil and go off in a completely different direction. Right, so they had this radioactive source that was generating these positively charged particles. They're fired at the gold foil. Most of the particles would go straight through the gold foil, come out the other side going almost the same exact speed they were when they went in. But some of them went off at really predictable angles. And so this is actually what turns out that what he was seeing was these particles were hitting something and bouncing off. Most of them were making it straight through without running into anything. Some of them would hit something and go a different direction. So Rutherford came up with what he called the nuclear theory. So at this point in scientific history, they already knew that cells existed. They already knew that cells had nuclei. So they basically said, okay, well, these atoms have nuclei too. They didn't know what the nuclei were, which is why we use the same word for two different things. It's confusing, but he was trying to be consistent, actually, with the science of the time. Well, okay, cells have nuclei, so do atoms. What he was actually seeing was that most of those particles were going straight through the electrons. So the nuclear theory is these four ideas. Almost all of the mass is concentrated into the nucleus of an atom, which is a really, really small volume in the middle of an atom. Leonora? Partly. We'll actually get into quantum here in a week or two. And that's actually where they dress it up using quantum terms, but that's related to it. But yes, in theory, if you were able to get your atoms aligned in just a certain way, and you might be able to pass through a material without actually running into any of those atoms, as long as every one of your atoms managed to avoid every one of the atoms in the material.
Theoretically.
It would basically what would happen is that you can't actually do that with numbers this large because they're not all arranged perfectly. And it turns out that when you actually touch something, you're actually not touching the nuclei, you're actually touching the electron clouds around the nucleus.
Actually touch anything.
Exactly.
It's like space around them.
And that's these electrons, because if you have atoms in your skin and your atoms have electrons around them, and then this material here is made up of atoms that have electrons around them. What do electrons do to other electrons? They repel each other, right? Or the same charge repels each other. So when you actually touch something, what you're actually feeling is the electron clouds from your hand running in and pushing back against the electron clouds from the material. So in theory, you could avoid the nuclei if you phased everything just right and stepped through a wall. However, you wouldn't be able to actually pass through the electrons, because the electrons are actually what are taking up all the space.
So the electrons reacting plus the explosion.
Potentially, yeah. And just for an idea of scale, anybody been to a professional baseball game? At least been to a baseball stadium. If you can picture standing on the pitcher's mound holding a baseball. The baseball is the size of the nucleus. The rest of the ballpark is the size of the electrons. So very, very small compared to all the electrons. Bryce, that's all your hand?
So with this electron cloud, would it change through pressure with how close you get? Sort of like magnets where you like push them together, get closer.
Turns out, yes, we can actually look at the shape of these electron clouds, and they actually do change based on other charges around them. Again, getting into quantum stuff, and that's my jam. That's what I went to grad school for, was talking about quantum mechanics and calculations. So when we get to orbitals, that'll make more sense, hopefully. So if all of our positive charge and all of our mass is in the nucleus, the electrons are so much smaller. Remember, they're 2,000 times smaller than a hydrogen atom. So by mass, but they're pretty much all of the volumes. And so the nucleus has to have a positive charge. And the other thing is, if the electrons exist as these tiny discrete particles, discrete meaning that they have to have individual particles. It's not a plum pudding of positive charge where you just have a random amount of positively charged stuff, bread. You actually have a discrete number of what they call protons. The proton, they just came up with that name as a positive electron. So something with a positive charge, it made more sense to Rutherford that there had to be a discrete number of them. When it came up with the way that they could count electrons on some of the smaller atoms, some of the smaller elements, you always wound up with a discrete number for the positive charge compared to the number of electrons. So you could have a discrete in the mathematical sense doesn't mean discrete like quiet about something. It means integer number. So an integer number of protons, an integer number of electrons. Basically, we're starting to come up with the pieces that we put together to make all the different types of matter. So if you wanted to go back to Aristotle's idea that if you get infinitely small, you just buried small amounts of the four main elements, really, you can get all matter on the periodic table by burying three types of matter: electrons and protons. And then the last thing was they knew that helium had two protons. They knew hydrogen had one proton. But helium wasn't twice as heavy. It was 4 times as heavy. So there had to be something that had extra mass. But it couldn't be something that had a charge, because they knew that your negative charge was concentrated in the electrons, your positive charge was in the protons. So they had something that had mass that wasn't charged. which they called neutrons. Literally for neutral electron, just like proton is based on the same root as electron. Right? So those three types of matter, protons, neutrons, and electrons, mixed together in different ratios, gives us everything on the periodic table. Basically, all matter that we can see, that we can measure, is a mixture of protons, neutrons, and electrons. All right. We'll end there for today. We'll talk more about how we can count those and everything and how the periodic table works on Monday. Quiz this weekend will be some more practice with conversions.